Welcome back. So in this video lecture, you will understand about the tracking of the particle using the inverted microscopy, right? So in this lecture, you will understand uh, first of all, how you can capture the images of the particles in the uh, you know uh, a given suspension, right? And later you can use the images, to understand the trajectory of the particles, how they are moving about, right? So using the image J, you will understand how you can get the perform the trajectory and get the information about the displacement of the particles, right? So, couple of my students, Vishal and Chandrasekhar, will be showing you the demonstration part in this video. Thank you.
My name is Vishal Singh Pavak. I am a PhD student in the Department of Chemical Engineering, working under the supervision of Dr. Manikandan sir. Today, I will demonstrate particle tracking using inverted microscopy. Initially, I will provide a detailed explanation about the microscopy, and the later part, I will show you the working of the microscopy software. And then after that, one of my colleague will explain the particle tracking part. Welcome everyone. We are here to demonstrate the particle tracking analysis using inverted microscopy. Here we have inverted microscopy, and we will cover the component parts of the microscope and how to prepare the sample and the tracking path. First, check both the ends securely plugged in. Thus, we will check that both the plugs are securely checked in and the connection is secured at both the ends. And we will remove the microscope dust cover, hold and store to a spare stool for or tray benching. Now, set the main switch on. Main switch is on, and once the switch is on, you can observe that the lamp will be illuminated. Here you can see, and if using the system for fluorescence, plug this cable and switch on the fluorescence power box. On the right hand side of the base, from here, lamp intensity can be varied. It's good to be leave the dial rotated to the lower side, lower slice intensity. This will ensure that the user's eyes are protected before reading the light intensity and can be seen at the top of the base. On the left hand side, uh, shift this shutter above, shift this shutter above for the fluorescence and down for the normal microscopy. Now I will show you the filter attached to it. This is at the blank position for instant light. This is a green filter in which emission is blue and excitation is in red color. And this is a blue filter in which emission is blue and excitation is in green color. Here, this is the sample stage where the lenses are below uh, the sample stage. Using the rotating nose piece to adjust the microscope to the 20x position, don't handle the objectives themselves as this could damage the microscope. I have already prepared the slide and placed the sample on it, as you can see here. Now let's position this slide onto the sample stage that we already did. Notice how that light passes through the sample from the underneath, providing clearer image particularly for the thicker samples. On the right hand side of the instrument, here are the x and y axis to move the sample stage, and the height of this stage is fixed in this instrument. Like that, you can move the x and sample at the x and y. direction. Next, you need to adjust the interpupillary distance. If you look through the eyepieces and see two images, the CD2 images, the interpupillary distance is not correct. The correct it, they slide the eyepieces close together or further apart until the two fields merge to form a single circle of light. The and in that case, the interpupillary distance is now correct. Uh, Use the coarse and fine focus knobs to focus the image as much as spectacle working up to at least 40% for text magnification. Only the fine adjustment should be required once you have established focus at lower magnification. To attain a sharp image, based on your eyesight, rotate each eyepiece diopter to 0 and adjust each eye individually until the image is most in focus. Then move on the next eyes. The right hand side eyepiece contain a graduated cross line reticule which needs to be sharply focused. The user right eye ensure that the graduated axis is in the east-west position. Now we have set the Leica microscopy and open the software. Let's move forward with our experiments. Today we will observe the Brownian motion of stained polystyrene particles and the platinum coated polystyrene particles suspended in water and record a video for further analysis. Since these particles are stained, they will be clearly visible under the microscopy. We can now adjust the focus to get the clear view of the particles. The image format, as you can see here, and the live format are set as default at 2048 and 1546. Initially, the screen will appear black. To get a clear image, I first adjust the X, Y, and Z position of the stage to locate the sample. Once the sample is in place, I move the slider to direct the light back to the camera. If I am already in live mode, the image will appear immediately. Otherwise, I click on live to start capturing the live feed. At this stage, I want to first show you the grayscale image before moving to the fluorescence image. To do this, I click on the grayscale button. Grayscale imaging help in understanding the overall contrast and structure of the sample without the influence of color channels. This is useful for setting the correct focus and exposure before switching to the fluorescence microscopy. Now that we have a clear grayscale image, let's move to the fluorescence imaging. Fluorescence imaging allow us to highlight our sample. By activating the fluorescence mode, we can observe how the stained particles emit light under excitations. Here I will turn on the appropriate channel to visualize the sample. You will notice an immediate enhancement in the visibility of the particles compared to the grayscale mode. To fine tune the image quality, I will adjust the exposure time, increasing it to 100 milliseconds. Provides a good range up to 1900 grayscales. If I see areas of over exposure, I can reduce the exposure time or adjust the intensity of the fluorescence to maintain a well balanced images. This is the histogram button located in the image display window. I am going to go ahead and activate that, and this histogram will give us a graphic demonstrations of the number of pixels on the y-axis at each grayscale and across the x-axis of the detector. This is helpful because a pixel on the camera that creates the pixel on the image is ultimately limited by the range displayed here. If we collect more photons converted to electrons within that pixel, then ultimately it will overflow, and as the electron exceed that capacity, we both lose both informations and the attractiveness of an image. So we want to operate within that range and avoid any saturation. If I maximize the photons going into the system, uh, we see these huge areas displayed in red. These are our saturated pixels, where the pixels are just overflowing with electrons. To fix this, we need to reduce our exposure time to get back within the range of the system. Alternatively, we can also reduce the number of photons entering into the exposure time to maintain optical image clarity. We can also capture a series of image for advanced analysis. The capture image button takes a single snapshot, while the capture series or capture image button record multiple frames of the time lapse studies. Additionally, I can toggle between grayscale and pseudo color modes to enhance the visualization. Now our image settings are optimized. Let's observe the movement of these particles. As you can see, the particles are undergoing Brownian motions. Here you can see a random movement caused by continuous collision with water molecules. These movements follows no fixed path and is influenced by particle size and surrounding fluid properties. Now let's record this motion for further analysis. Our left hand side of the software interface, we have the video recording options. I select live view already to ensure the particles are in focus and adjust the frame rate to 3 fps for smooth tracking. Here you can see the live movement of the particle. I will now start recording. I simply click the record button. The recorded footage will be useful for detailed particle tracking analysis. Now let's play the fluorescence video that I have recorded live. You can see that how the particles are moving and how fluorescence enhances their visibility, making it easier to analyze their motion. After recording, we can use the software like Image and MATLAB to track the particle tracking analysis and calculate diffusion coefficient. This help in various applications including nanoparticle research, drug delivery studies, and environmental monitoring. Before concluding, I would like to show you short videos of Brownian motion of passive particles. This clips highlights how the particles moves randomly due to molecular collision. You will notice that smaller particles move more rapidly than larger ones. Demonstrating how Brownian motion depends on particle size and surrounding fluid properties. With that, we conclude these demonstrations. We successfully observed Brownian motion under the Leica microscopy, recorded a video for further analysis, and explored the importance of fluorescence imaging. These simple yet powerful techniques provide deep insight into the microscope particle behavior.
So now we will see how to track the particle system and do the particle tracking using microscopic videos or microscopic image analysis. As you can see here, I'm having one video which is showing the motion of the different type of particles. You can see here, these all are the most showing the different motion of single particle, double or triple particles. Actually, these are hematite cubic particle that we use for some of our analysis. Now, I'll show you how to do the tracking of these particle system. First of all, what we have to do, we have to go to the Image, as the Image is an open source software. Anyone can use this software. It can be download from the Image website directly. So from here, what you have to do, you have to go and import your file. So now I'm going to import my file as an ABI. As I showed you, this is a video, right? So I've already mentioned the extension for the ABI video, or you can take this from here to let's open this system. Now your video is completely open here in the and you can see this video is in the form of each and every frame. As you can see here, this video is having 500 frames, total 500 frame. We can say 500. Just now as the 500 is very huge amount for the demonstration purpose. So what we have done, I have already actually done the image sequencing. Image sequencing is what whenever this video, the image sequencing basically define the formation of the number of images from the video with respect to time. They give us the image sequencing. For that, what you have to do is you have to go to save image and go to image sequencing. Using this, you can actually save your video in the form of image. So as you can see here, this is the path that I'm going to grab, or let me change this path again to show you. So yeah, so I'm going to make another folder, experiment 2, right? So now this is a path to save this image sequencing. Now format, if you wanted to change, you can change format from here: GIF, JPG, PGM, PNG. Number of, usually I'm taking TIF format, and here I'm clicking use the slice label as a file name. So there, the slice label means the time of that particular plane will come as a image name. Okay, now you can see here, this is showing the progress, continuous progress. When this complete bar is full, it means your video is converted into the image sequencing. Now let's wait for this. After this, I'll show you how to go and how to do the tracking analysis. This is almost about to complete. We have to wait till this, otherwise we will not able to do what all data will not come in the picture. As of now, you can see now this image sequencing is done. That gave the directory for experimental. As you can see here, this all video is converted into the one each frame. Now, as you can see here, the label is with respect to time 0.03, 0.06 seconds, 0.09, 0.12. So the time is a multiplier of, or you can say addition of 0.03. Now, the time interval between a frame is 0.03. All right. So now let me close this video. Now what we'll do, we'll open this image sequence. We'll import this image sequence so that we can do the image by image tracking here. So now as you can see, so now this is showing the directory from where I wanted to call the sequence or our image sequence. So experiment folder 2. Let me select this. So this is our new. Now this one which type of, so make it default. It will automatically consider whatever the image type, tips, JPG, and whatever it is. Now this saying from where to where you want it to count. Okay, 1 to 500 as the total images was 500 I showed you. So I'm saying okay, call 1 to 100 only, right? Now just click on the open. Now you can see here. Now, so this is how we call our image sequence for the tracking analysis. As you can see, number of images showing to 100, and to one image timing is here. You can see 0.03. Total pixel value is 1024768. Currently these images are in RGB mode, and this is showing the size of our images. All right, now we'll move towards the tracking for the particle. So there are two different mode you can see. So I will show you how to do manually. Apart from manually, there is other tools are also coming for tracking analysis. So that those tool also you can use. But here I'm just showing you manual tracking how to do. So for manual tracking, what we have to do is go to plugin. There is one plugin name called mTrackJ that you have to download from the image website. That is readily available and free of cost. But the as a open source plugin, this is available. So one can use this is a manual tracking. One can use the automated tracking system, which is also available in the form of plugin on the image website. Okay, now let's go to the mTrackJ by, so actually this plugin already installed in my system. So I'm just going to open it. Now this is saying add. All right. So after this, so this is the window which will show you the different option. Clear from using clear option, you can clear whatever the tracking you already have. If you wanted to load some other tracking, you can load from here. You wanted to import your data, can input, save, add. You can add one by one. Suppose there are number of particles, so I wanted to track each and every particle in a video. So by add option, you can do hide. If you wanted to hide, you can hide. You want to delete something, you can delete. You can move or merge. A number of systems depends on you. So now let me go to the add, or sorry, let me go to the add, and let me add the particle per particular particle system. Let me suppose I'm going to choose this particle. Let me see how the what is the behavior of this particle, right? For till 100 images. Okay, so for that, what you have to do is you just go to the particle, keep your cursor in the mid of the particle, because most more over the time, whenever we are saying we are doing the tracking, for tracking, so there are two different type of motions I'm trying to come in the picture. As our particle system here, this is an active particle, so moreover they are showing a directional motion, right? So whether they will show the linear motion, they may show the sometimes circular motion, depends on the different conditions. So in that case, what you have to do, always you have to take your cursor into the mid of the particle. Then you have to click. In case suppose if your particle is not properly visible, then go to this lens time or magnifying lens glass icon. And this your cursor will become a magnifying glass. Using left click, you can zoom your video like this, right? Suppose if you want to zoom it out, right click. Using right click, you can zoom it out. So now, okay, now I have zoomed this particle, so that I can track this particle very nicely, and I can click wherever I wanted to do. All right. So again, by choosing add menu, now you can see now. So this is how I'm tracking. Okay. So in the mid, so we our cursor must click in the mid of the particle, right? Or you can say in the center of the particle. Then only you can get some good data. You can see here. So this path is continuously visible to us. So this is how our particle is moving. You can see here. So I'm clicking in the center of the system. So with this manual, with this tracking, so what will happen? The track or the motion of the particle will be, the tracking of the motion of the particle will be in your hand. While if you are going to use automatic one, so it's depend on the how the plugin is working, right? So here you can see. So I'm still so far we have done the 34 images. As we have 100 image sequence, so we have to click 100 times on the particle, so that it can give us the motion properly. As you can see, this particle is moving here and there. So this carefully you have to do. That's why we have done the we have zoomed the video using magnifying option, so that we can easily see, and we can manage the system and do the tracking. So now this is about to complete. So you can see we have done the yeah. So now we have done the complete imaging. As you can see, this is the path which is showing by the particle, or particle start moving from here and it moves up to here. Now what I'll do, I'll click on the measure, so it will measure all the data set. You can see here, right? So it measures the pixels or all the pixel values and each and everything. So there is two different ways to do this. One is on the basis of the pixel that I have shown to you. Another way is another way is what you have to do is, before doing the tracking, you can give the length scale or the pixel values to the system. Okay, so for that, what we have to do is we have to go to the analyze, and we will click the set scale to set the scale. Let me show you the another type of things that using which you can actually you can get the so this is how you can actually give the values, your distance or the pixel values to the system. So what I've done, I'm just going to draw one line from here to here, whatever the scale we are getting through the microscopic images or video, and then I'll go to analyze and I'll set the scale. As you know, the pixels according to the line or as per the line is covering is 212 point something something, right? So now I know the distance is 25 micron. All right. So now I've wrote 25 and unit is micron. So remember in image A, micron will come in the form of your M. Now with the global option, you can make it global. So now your scale is 8.5334 pixel per micrometer. So now one can use this approach using scaled value. You can actually measure the actual distance. One can use the pixel, depends on the pixel analysis. It's totally depend on which type of analysis you wanted to do. So what actually we have done is we always using the distance approach in this case. And so this is the data that we got from the Amtrak tracking. So what you can see here, this is showing the uh, tracking ID. TID is mentioned for the tracking ID, as you see. So ID at the time we were clicking was 1. So tracking ID 1 means this is following a single path in the our overall image, right? And this is showing total 99 points we have actually calculated. Because why? So as you can see, the 100 points we are just showing 99 because first is not considerable. That's why. So the minimum X pixel was this, maximum this, and standard deviation. So this data, all the data you wanted to save, you can save using save option to file, and you can save wherever you wanted to save. Let me save it in this value on the name of uh, data, right? Now, okay. Next data is this. So for tracking analysis, actually we need the data of X and Y and time data that we need to know. As we know, this is a 0.03 time lapse video, or difference is 0.03. So we actually need X or Y data. So here I'm showing you in the form of pixel. All right. You can save in the form of micron or distance. So now again, we can save this data, right? So I'm giving this name data to, all right. Now, so now using this data, we can actually calculate the MSD, which we can call mean square displacement of this particular particle. So for that, what we have done is we already have a MATLAB code, our own MATLAB code written inside our lab. So in this MATLAB code, what we have to done is we have to call wherever the data we have saved. So here I'm showing you the previous written program and all. So this data is already saved in the form of by the name data2 in Excel format. So I'm actually calling Excel here, Excel file. Now, so with time I'm giving, this is the time distance and everything is in the data form. So I'm going to calculate the MSD, mean square displacement, and velocity, and plot of velocity and mean square displacement too, and diffusion coefficient. Okay. So now let me run this program. So you can see here this program is in running condition now. So see, this is the MSD diagram showing the linear motion. So as I showed you in the video, the particle is showing the linear motion. So MSD is also coming linear. And this is the velocity which is around the mean values of the displacement. All right. Also, apart from this, you can get this. It's totally depend how you see how your code is running. You can get in the form of data also. You can see MST data, time data, velocity data. It's totally depend on you. So this is how you can done the tracking, and you can plot the mean square displacement of your particle system, active particle system. Thank you.